Okay, while we are waiting, like, are there any questions about like homework one? I'm sorry, homework two or the incoming quiz? Just put it in the chat window. Okay. No, I don't think so. Greedy is just uh, I think quiz two is basically going to cover. It's very similar to like the practice quiz you already received. Um, so basically, I'm gonna just talk about like some basic stuffs about greedy algorithm today. Okay, I think we should probably get started and welcome. So today on greedy algorithm. Before we start, I'm just like before we take a look at today's question, I just want to share some of my personal opinions, personal thoughts about like greedy algorithm. Like greedy algorithm is really similar. It's like it's so similar to like optimization problem. Like when, for example, if there's a quadratic function, if you want to find the maximum value of it, you just if you know like there's an algorithm called gradient ascent or gradient descent, whatever it is, it's just like you're climbing a hill, and once you're at a position, you find a maximum gradient and you go for that position, and you climb that hill one step by step until you reach the optimal value of that of the quadratic function. And greedy algorithm is kind of like the idea of greedy algorithm is kind of similar. It's like it decompose like a by the way, like gradient ascent and gradient descent can only guarantee local optimum. It cannot guarantee like global optimal value. But if if the problem is like a convex or concave function, then like this quadratic function, it is concave, then I'm sorry, it is convex, then like you can use like greedy algorithm. So I'm sorry, you can use this gradient descent. So greedy algorithm, greedy strategy is similar to this kind of idea that you can decompose like a whole problem into different subproblems, and you choose like the optimal value for each substep, and you will reach the global optimal value. So let's jump back to today's problem. So let's take a look at the question one. Basically, it's minimize customer waiting time. I'll just give you guys 1 to 2 minutes to read the question. It's very simple, and then we'll just get started. Oh, by the way, I may have to like close the video because I don't know why the CPU get overheated when I turn on the video and sharing the screen meanwhile. So I may have to close the video. Okay, let me just briefly explain this question. Very simple. We have like N customers here, and like they arrive at the auto shop. Let's denote this customer as C1 to Cn, and they arrive at the auto repair shop and they want to get their service done. So the I's customer will take Ti minutes. Like basically, he will take Ti minutes to finish his own business, and you can service exactly one customer at a time. So the objective of this problem is that we want to find an order so that we can minimize the total waiting time for all the customers from C1 to Cn. And This is our question, and let's take a look at the very basic example of that. So let's say we have like 4 customers here, and the first customer will take 4 minutes. The second customer takes 3 minutes. The third take 10 minutes, and the fourth will spend 8 minutes in the auto repair shop. And so the waiting time for C1 is 0, since once the customer get into the shop, the shop will provide service immediately, so he don't have to wait. And the second customer needs to wait until the first customer finishes business, and so on, so on. And third customer need to wait all the customers in front of him. So basically, for the ICE customers, he has to wait until all the customers in front of him has finished their business. And then, yeah, basically it's about greedy algorithm with lowest weighting. Yeah, very basic. But for this problem, we want to basically prove this stuff. Yeah, thank you for that. And so like for here, the total waiting time will be 28. Since like this is the first customer here, second customer 7 minutes, and like what if we change the order of it, like just basically change the order that these customers come in. So like for the first customer, we let the C2, who will spend like 3 minutes, and the second customer will spend 4 minutes. Third customer, we will let like this customer who will spend 8 minutes, and then we let the customer with the longest service time in. Yep. And so here, like C1 will basically wait 3 minutes. C4 will again wait 7 minutes, but for C3, he will only need to wait like, I think it's 7 plus 8, so 15 minutes here. So the total waiting time using this order is 25 minutes, which is better than the 28 minutes. So for this problem, instances here, just before we want to like go through like a greedy algorithm, we just see through what are the instances here. The instances are these customers C1, C2 to Cn. Okay, and the solution format is basically we want an order of n customers. And the only constraint here is like you can only the only constraint here, you can only service exactly 1 customer at a time. So this is a constraint, and our objective is to minimize the sum of the total waiting time for all the customers here. So this is basically our problem. This is basically the same as what I just wrote on the slide. So the time taken to complete a job added to the waiting time of all customers whose job is done after this. So the key idea is to do the shortest job first. And here is since like T2 will be added to the waiting time of C1, C4, and C3, and T1. The service time of like the customer number 1 will be added to the waiting time of C4 and C3, and the service time of the fourth customer will be added to the waiting time of C3. Since like C3, customer 3 is the last customer, so his waiting time will not be added to any other customers. So like similar to the lecture, we have like different ways of proving this. The first way of proving this is by the exchange argument, the exchange lemma we have. We let G, just 1 sec. We assume that G is our greedy strategy or greedy solution, whatever you name it, and G1, we have G1, G2, Gn. These means like these are the kind of steps or the choice we have for this greedy strategy, while the OS means like other solution, other strategy, any kinds of combination of strategy, as long as it satisfies the condition, it satisfies the condition that we cannot provide service to a customer twice. And so the exchanger argument is that like there are basically two cases. Two cases, G is the greedy strategy and OS is the other strategy. The first case is the first step that greedy strategy takes is the same as the other strategy here. So basically what we want to do is we want to see that if we exchange the first step of other strategy with the greedy strategy of the first step of the greedy strategy, we want to show that after the exchange, the performance is at least as good as the original other strategy here, original OS here. So what we want to do is for the case one, since O1 equals G1, then they're definitely since they're the same, so they're as good as each other. So let's take case two. So case two is basically O1 does not equal to G1, and we will change the order of OS by exchanging O1 with OI. Let's assume this is not O5, this is OI, and OI is actually the first step that a greedy strategy will take. Yeah, like basically go through this lemma, and then and there's another like way of proving this thing later. So we will change the ordering of the other strategy by exchanging O1 here. We exchange the we exchange for the other strategy, we exchange OI with O1. And then here is the here's the result after the change. Let's take a look at it. So like the waiting time of OS prime here equals the waiting time of O of S minus, so right now we assume like there are K jobs between, K customers between O of 1 and O of I here. And so since like our greedy strategy, the O of I, which is G of 1, is the customer with least amount of service time. So for all the customer here, they will spend less time waiting. So we assume they are K customers. So here is they will definitely spend less time waiting. T of O1 minus T of OI. And we assume that this T basically means the service time of a customer. And we want to take, and we assume like the service time, the sum of the service time from O2 to O4 is D. So basically here. And so for O of 1, for O of I, since like before he has to wait until all the customer in front of him finish. So right now when he will be moved to the first customer, he no longer has to wait a minute. So the service time, the waiting time for him will be minus D plus TO1. And for O1, since he will be moved to the original position of O of I, so he will wait more time, and here is the waiting time here. And this basically equals to WT O of S minus K plus 1 TO1 minus TOI. And since this is a positive number, this should be greater or equal to 0 here. Since like because of the greedy strategy, T TOI is the smallest among all. So we can basically prove that W wait time of OS prime is less than wait time of OS. And since we can prove the first step, then we can recursively apply the same steps and from like the second step, the third step, the fourth step until the end step. And finally, we can conclude that the greedy strategy can lead us to the optimal value of this problem. I think this is quite obvious, since like this is a really simple question. So like the other way of like proving is, this is basically repeating what I just said. The other way of proving is greedy stays ahead argument. So basically, we want to show that the greedy strategy will always maybe cover more or stays ahead of all other kind of strategies, and we'll use induction to prove it. Very simple. I just want to show like the basic steps you're gonna write in your homework, in your future quiz, if there is a similar problems about the proving of like greedy strategy. Okay, so here we let G1, G2, Gn. Basically, it is the greedy solution or greedy strategy here. This is like any other strategy. It can be any combinations, doesn't matter. And one of the things is, since this is a greedy strategy, then it has to follow this, that this is our greedy strategy. And we let GK and O of K denote the total waiting time for the first K customer serviced by the greedy and other solution respectively. What we want to argue is this for K between 1 to n. So for the base case, it's quite simple, since GK, when K is 0, customer doesn't have to wait, so they are both equal to 0. The waiting time for the first customer is 0. And let's take a look at the hypothesis here. Since like, suppose we have like G of K. Suppose we have like G of K less than equal to O of K for K between 1 to n minus 1 here. So that's the G of n is basically this function here. And O of n is basically the following function. So by induction hypothesis, we already concluded that this this holds Gn minus 1 less or equal to On minus 1. This is our induction hypothesis defined here. And then we want to, and then this is the second part of the equation. We want to prove this. Again, like this is again like quite obvious, since because like the greedy strategy that we use. Basically, since let me just write this down. Since the sum of the service time for the first n customers should be the same. And since like the TG1, TG2 to TGN minus 1 is the first n minus 1 customers with least amount of service time. So we can also conclude that the sum here is less than the sum here because of the strategy that we apply on this problem. So that basically means that G of n is less than O of n. And since because of this, we can always prove that the greedy strategy will stays ahead of the the other strategy here. And basically, we already finished the proof. Okay, so are there any questions so far? Okay, let's move on. So like the second question is a little bit more interesting. It's again like a greedy algorithm. We use greedy algorithms to solve it. So I'll give you guys another like 3 to 5 minutes to take a look at it and think about what kind of greedy strategy we should use and how we should basically prove it. Also, for this question, we're assuming that all these intervals, let's say S1E1 to SMEM, will cover all the points. So you don't need to worry about whether they can cover all the points or not. Yeah, we'll basically cover like the greedy algorithm mentioned by Hadir, and basically greedy algorithm is like once you found like the normal way of solving this algorithm is like NP hard will spend a lot of time, they will probably start thinking about using greedy. And like for greedy, you need to like be greedy on something, and you would try different greedy strategies, and see whether they can work. And I don't think cover the most unselected points is a good idea. We'll cover that later. Yes, I think Simon is like basically, yes, I think Simon like is kind of correct. Yeah, is correct. So it's not about the coverage, just we assume that like these intervals will cover all the points. Just basically want to find the minimum number of intervals that will cover all the points. For example, here, if we choose all the intervals, then it will definitely cover all the points. But we don't have to like choose all the intervals. We only like need a subset of that like total interval set to cover all the points Yes. I think Hadir, I'm sorry for my pronunciation, but if you choose like the longest header, oh, thank you.
Yeah, no problem.
Okay, thank you. Sorry about that header. I think you're right. If you pick the longest one, if you pick an interval that will cover a lot of points, but what happened if like the longest interval has already covered another shorter interval, like the second longest interval inside it, then we are picking like the same thing again. So that will waste like one interval, one spot here. Okay, so let's start look at the question. Oh, I'm sorry. I need to reshare the screen. I don't know why like this always happen. Just 1 second. Okay, let's take a look at the question here. So what are the instances? The instances is basically all the points here. Let's say this is x1, x2, and blah, blah, blah to xn. And all the intervals. Basically S1, E1 to SM, EM. So the solution format is basically we want a set of intervals, the minimum, the set of intervals that can cover all the points. Solution format and constraints. Not really a lot of constraint, except like we can use an interval twice. And this is something we will never do. So the objective is basically find the minimum number of intervals. So let's take a look at the strategy that was mentioned by, I'm not sure what, one of the students in the chat room. Like we will first find, we will always like try to find an interval that will cover as many points as possible. So this is, for this example here, we have like 5 different nodes. I'm sorry, 6 different nodes and 3 intervals. This is, we call this I1, I2, I3. And we can see that I3 is an interval that covers 4 points. So this is the first interval that we choose. And then we take a look at I1. It covers 3 points. And then we finally take a look at I2. So this way we pick 3 intervals, but in fact, obviously we don't need 3 intervals. We only need like I1 and I2. We don't need I3. So let's take a look at another strategy here, another greedy strategy here. So seems like we can think of like this. We want to organize order points. So we organize order points in a plane and like put them from left to right. And this is x1 is from the left and x6 is on the right. And let's say like, I'm sorry, let's use another number, xj here, and this is xj plus 6. Yep, and let's assume like this is xj here. This is the first point that is not covered so far, and we want to find an interval that will not only cover xj because one way or another we have to cover xj here. We cannot just skip this. We cannot just skip this point. We cannot just skip this point and say, oh, this is the longest interval here. So we need to find an interval that will cover the first point that hasn't been covered, and will also cover as many points as possible. So for this example here, we will first we will choose this, since this is the first uncovered node here, and since there's only one interval that cover xj, so we will first choose this one here. And then we cover this node, these 3 nodes. And then from now on, we see this. this is the first uncovered node right now. So there are basically two options for it. One is this and one is this. So since this interval I3 will not cover xj plus 6, this I2 will cover xj plus 6. This is the interval that we want to have. So right now we already cover like two intervals. I'm sorry, we use two intervals to cover all six. Sorry, to cover all 6 points here. So basically, it is like this. We have points here. When we're given like multiple choice here, let's say this is the choice, and if there's something like this or something like this, we will choose the latter two. We will abandon the first one. And if there's something like this, then there's no reason that we choose the latter one, since it will not cover this point. And if there's something like this, since this second interval here will not cover this point, and our objective is to cover all the points while maintaining the minimum number of intervals. So it does not satisfy the condition, that satisfy the requirement. So we'll still pick this if if this is the situation. And so yeah, this basically is what I just mentioned, what I just wrote on the slide. We first sort all the points by their x position, and we repeat. We assume xj is the first uncovered point, and we pick the interval that will cover, not only covers xj, and will cover as many points as possible of xj plus 1, xj plus 2. Just basically cover as many points as possible starting from xj. So basically, we'll use like greedy stays ahead to prove the correctness of this greedy algorithm. So there are like a few steps that probably will be helpful when you are like trying to prove greedy algorithm, especially using greedy stays ahead. And so the first step is to define a progress measure. What I mean by progress measure is how you're going to measure the progress of greedy, and how you're going to measure the progress of the other strategies. So since we want to show that the progress of the greedy will always stays ahead, we want to like set up a criteria for the kind of progress measurement to show that our greedy strategy will always stays ahead of the other strategies. And the second thing is we want to define some way of ordering all the choices of other strategies and to line up with our greedy strategies. This might seem a little bit hard to understand. I will basically illustrate it later in an example. And then like after we have set up a criteria and we line up all the choices, and then we want to apply the induction. We want to like prove by induction on I that the number of choices that after I step, the greedy strategy will make at least as much progress as as other strategies here. And the final step is basically using the previous step to show that the greedy strategy is at least as good as other strategy. Basically, 3 and 4 is the same here. So are there any questions so far? Okay, so let's take a look at the progress measure. So the progress measure here is we want to show that the points covered by the intervals, all the intervals of the other strategy is a subset of points covered by intervals of the greedy strategy. So basically, we want to show that greedy strategy will cover more points. with the same amount of the same number of intervals. And they basically, yeah, this show like number of intervals in OS will be larger than the number of intervals in greedy strategy. This is our progress measure. We want to like show that the greedy strategy, well, the progress of the greedy strategy will always stays ahead of the progress of other strategy here. So secondly, we define some way of ordering all the choices of OS to line up with the greedy strategy. So like there are different, so here like there are different intervals here. Let's see this. We want to give them like an order. We want to order them by the start of each interval. So basically for here, this is the first, this is the second, the third, the fourth, the fifth, 1, 2, 3, 4, 5. We want to give them like an order so that we can line up the greedy strategy with the other strategy. Otherwise, like if you say this is 1, this is 2, then it's so hard for us to compare the greedy strategy with the original, with the other strategies here. So the second step is to line it up. We basically sort if all the intervals provided here is not sorted. Basically, we need to sort all the intervals by their start of their start. And right now, the next step is we want to prove by induction on I that the number of choices that after I steps, greedy strategy has made at least as much progress as other strategies. So for all I want to show that points covered by the first I intervals of other strategy is a subset of points covered by the first I intervals of greedy strategy here. Just basically greedy strategy will cover more points with the same amount of intervals it has. So base case, inductions always start with base case. The base case is true by our choice of S1, E1, since we only picked an interval that covered most points starting at the left. So if this is the, I'm sorry. So if this is the situation here, we'll always choose this one. So the base case always is always true. Then we take a look at the induction step here. Let's say it holds for I, and want to prove like we want to like induce on this I+1 step here. So here, what we mean by is it holds for I is that the points covered by the first I intervals of other strategy is the subset of points covered by the first I intervals of greedy strategy. So let's assume like these are the points. So first I, these are the first I intervals of the other strategy here. Let's say OS. And these are the points that are covered by the first I strategy. And this is, we let xj to be the first point that is not covered by the other strategies here. And let's say like si+1 to here, this si+1 star. Just 1 second. What do you mean by starting at the left? I don't quite follow you. Could you be more specific? Like, which is starting from the left? The last slide. Okay. So what is starting from the left? So this greedy strategy is basically we line up all the points here. And for each point, there's let's say this x1, x2 here. We just line up these points from left to right. And we start with the first point that is not covered so far, which is for this point, it is x1. And we want to find a interval that will not only cover this point and will cover as many points as possible, starting from this first uncovered point from the left. So yeah. So this is what I mean by starting from the left. And since the base case is always true, since we will the greedy strategy is to pick an interval that will cover as many points as possible from starting from the left. So base case is true, and the induction step is let's continue with the induction step. So the induction step is basically the induction hypothesis is basically first I intervals. First I intervals of greedy strategy will cover more points than the other strategy. So there are like two situations. Before we go through this two like situations here, let's assume this Si plus 1 star E, this should be I here. EI plus 1 star be the I plus 1 step that other strategy take. So it can be any step. It can be this, it can be this long or this long. It doesn't matter. We just like assume they're like the other strategy. Basically, we can call it the stupid strategy that takes one step. So like for this step, it will cover all the points until XL. This is the I plus 1 strategy. We'll assume this is the I plus 1 strategy that the OS takes. So there are like either two conditions, either like the first I intervals of the greedy strategy has already covered all the points until XL. So this is the condition. It has already covered all the points here, or it cover let's assume the worst condition. It is exactly the same as the other strategy, or we can say the other strategy exactly the same as the greedy strategy here. This is the first I intervals here. And we assume that this interval here, this Si plus 1, Ei plus 1, is a candidate interval for the I plus 1's round of our greedy algorithm. So for the I plus 1 round, our greedy strategy will still choose this. So for the I plus 1 round, this is this will be all the points that we already covered here. We will also cover all the points until XL. So this basically shows that even it's the worst condition, the greedy strategy will perform at least as good as other strategy. It will always at least stays ahead or be the same as the other strategies here. So this basically prove that since we get the infection here, this basically proves that the greedy strategy is it's at least as good as the OS and it's the optimal value. Since OS here means like other strategies, all kind of other combination of strategies here. So basically here we finished the proof. So any questions? Okay, I see. I think everyone is understand the material good. So I'll just give you guys like one more question to think about. It's like a very classic algorithm problem that shows up a lot in interview questions. So we'll give you array of meeting room intervals consisting start and end times. This is just a question for you guys to think about. Let's say start one, E1. This is all the meeting. This is an array of meeting time intervals. Yeah. And to, let's say, SN, EN. We'll give you n intervals. These intervals means, so how can you choose SI plus one? It basically means that the even if greedy strategy choose the worst the stupid move made by the other strategies, then the greedy strategy is still as good as other strategies here, let alone we choose a better one. I'm sorry. If it means like even if the greedy strategy choose like a very stupid move at I+1 step, it is still at least better than greedy strategy and the other strategy. This is basically what we want to prove. We want to prove that the greedy strategy will always stays ahead of other strategies here. Yes, yes. It doesn't matter. It can be like this. So if for the other strategy it choose this, as long as it cover XL, if like greedy strategy choose the same, then it means like the greedy strategy is still at least the same as the as other strategies here. Okay, so let's continue with our some kind of homework problems. We give you like n intervals indicates the start time and end times of different meetings. We want you to find minimum number of meeting rooms to hold a number of conference rooms required for n meetings. So basically, if there's an overlap between two meetings, then we need two conference rooms. So basically, one would give you like n intervals indicates the start time and end time of n meetings. We want you to find how many meeting rooms required for these meetings. Oh, my bad. I haven't watched today's like recording so far. So I guess you guys already get the answers. Okay. Okay, so that's basically everything I want to cover today. And thank you so much. I will stay here for maybe another 5 minutes to answer some of the question. So thank you. Oh, which approach here? What approach? You can jump on mic if you want. I haven't looked at today's like recording. I always like watch the recording one day after this lecture. always use the single room greedily. Not sure about the correct. Always use the single room greedily. Yes, I think this is kind of my idea that we first sort the intervals by their starting time, and then we have like a heap that will output the that will be sorted by the end time of all those meetings. And then we will just pop them out and see whether it can fit into the current meeting room. Not sure about the correctness. Yes, if you can like, you can always like use like all the methods. I mean all the methods we mentioned today or in the lecture to prove the correctness, but having an idea about greedy algorithm is the first step. I will look at today's recording to see what's professor's way of solving this question. But for me, I sort the intervals first by their starting time and use a heap to output, I'm sorry, to contain all their meetings by their end time. In 3A from homework. Okay, just wanted to make sure that I was remembering. Yes, 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 because like for 3A, homework 3A, it is a DAG. So what you need to do is to, since this is a DAG, and that means the sink will not, the cost of the sink is always itself. And then you move one layer up to see all those nodes that points to the sink, and then to see and then to update the cost of that of all the nodes in that layer. So basically, first topological sorting, and then think about like the sinks and source, and update everything starting from sinks to source. I think this is probably the right strategy. Okay. Thank you. Thanks everyone. I always hold office. I also hold like office hour on Wednesday and Friday, and I found like some of the students try to enter my office hour room today and on Monday. So just check the schedule of all the TAs. Okay, I'll end this meeting. Thanks everyone.